Okay, so today's notes are on two variable inequalities. Our content objective is to graph two variable inequalities, and our language objective is to define terms including linear inequality, boundary, half plane, and test point. So the first term that I've already defined for us here is linear inequality, and a linear inequality is an inequality in two variables whose graph is a region on the coordinate plane bounded by a line. So basically this is just a linear function that instead of having an equals to has a greater than, less than, greater than equal to, or less than equal to sign. So we have to shade to demonstrate the region that would allow for all the possible values that would prove that inequality true. What I mean by that is we could have graphs that look like either of the two examples here. So when you have a linear inequality or a linear equation that instead of an equal sign has an inequality sign, you end up with a whole region that serves as the solution. So what happens when you graph them, you end up with a boundary line, which is what you'd normally think of when you graph lines. You have a boundary line or boundary, and this is the main line that you'd graph for your linear inequality, but all of the solutions for that set are actually the half plane. So this shaded portion is called the half plane, and that is actually all of our solutions. If there is a solid line, that means that the line was greater than or equal to or less than or equal to. So what that means is this line is part of the solution set as well as the whole shaded region. So for a linear inequality, you have a whole shaded region that's the solution set. If the line's solid, it includes the line as well. However, if the line is just greater than or less than, you end up with a dotted line, which means that line is just the boundary, it's not part of the solution. So when you have a dotted line, it's not part of the solution, it's just the boundary line, and then only the shaded region is the solution, or only the half plane is the solution. So this is the shaded side. So let's do an example so you can see more clearly what I'm talking about here. I want us to graph y is greater than 3x minus 1. So what I'm going to do here is start by making a coordinate plane. So I'm going to do my x-axis, my y-axis, 1, 2, 1, 2. So if I graph this line, I know my y-intercept is -1. I have a slope of 3, so I got 1, 2, 3 over 1. If I go the other way, down 1, 2, 3 over 1. Since there is a greater than, no equals to line, I know I'm going to have a dotted line. So I'm going to graph a dotted line here. So if I'm going to write out my steps, I'll do this over here. Step 1 is to graph the boundary line. And we graph this just like we graph any linear inequality that or any linear equation that you've graphed previously. The only thing you have to keep in mind is the solid versus dotted line. So if it's greater than or less than, it's dotted. If it's greater than equal to or less than equal to, it's solid. So I've done that. Then the second part I need to do is shade. And the way I do that, if it's in linear, shade half plane. There's a couple different things to keep in mind here. If it is in slope intercept form, so y equals mx plus b, which is what we have right here, then if y is greater than, you shade above. If y is less than, you shade below. So, and this, it goes for greater than, equal to, less than, equal to as well. So you could have the equals to lines, it doesn't matter. So in this case, since y is greater than, I would shade above, which means I'm shading up. So my solution set would include anything above this line here. So I'm shading lightly that way. So that would be my solution. However, if you are not sure which way is above and below, if you have a slow slope, you can also choose a test point. This also works if you don't have slope intercept form. If you had standard form, if you just plotted the y-intercepts and connected them, you can figure out which way to shade by using a test point. So what this means is you choose a point. So I'm going to choose, for this example, the test point 0, 0. That's usually the easiest one. You should almost always choose that one unless your boundary line is on that. So unless your boundary line is on 0, 0, you should choose 0, 0 as your test point. And then all I do is plug in for x and y. So I'm going to substitute and simplify. Sorry, I'll slide that down a little bit. Substitute and simplify. So I'm going to have 0 is greater than 3 times 0 minus 1, because all I'm doing is plugging in for x and y in my original inequality. So I get 0 is greater than 3 times 0 is 0 minus 1. 0 is greater than negative 1. That is true. So I should include the test point in my shading. So if the test, when I plug it in, is true, I include that point in my shading. So you can see 0, 0 is right here, and that is in my shaded section, which it should be since it passed my test. So let's do another example just to make sure this is really clear. So I'm going to flip the page and do a quick check. So I'm going to make sure this is really clear before I move on. So for our quick check, I want us to graph y is less than or equal to negative 2x plus 1. So try that on your own real quick. Pause if you need to. I'm going to go over it now. So I'm going to make my grid first and foremost. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so my y-intercept is 1. I have a slope of negative 2, so I go down 2 over 1, down 2 over 1, up 2 over 1 this way. Since it has an equals to line, I'm going to draw a solid line through those points. And now I know it's less than, so I'm going to shade below. So it's less than or equal to, so I'm going to shade below since it's in slope-intercept form. Again, if you didn't have slope-intercept form, or if you just want to practice with the test point I'm going to use here is, again, 0, 0. So if I plug in 0, 0, I get 0 is less than or equal to negative 2 times 0 plus 1. So I get 0 is less than or equal to 0 plus 1, or 0 is less than or equal to 1. That is true. So I shade to include the test point, which in this case is 0, 0. So I'm going to shade to include the test point, which is 0, 0. So I'm shading this way. So that's my answer. The last thing I want to talk about in our notes for today, make sure you write down any questions you have on this part, but the last thing I want to talk about for our notes today is also another type of two variable inequality, a absolute value inequality. So for this example, I want us to graph the inequality. I'll write it down here. So I have space y is greater than absolute value x minus 1 plus 2. So this ties back to what we practiced earlier this unit, graphing absolute value. So our first step is going to be plot the vertex. So in order to plot the vertex, I need to remember what the vertex is. So I'm going to give myself some space here. All right, so for this one, my vertex in this case is going to be 1, since I always switch the sign for my x value, and 2. So my vertex here is 1, 2, because I know h and k. So I go to 1, 2, plot my vertex. Then I'm going to graph the boundary line. So I know the slope here is 1, so I'm going to graph my boundary line by figuring out, okay, my slope here, since there's no a value, I know my slope is 1. So I'm going to go up 1 over 1, up 1 over 1, up 1 over 1 this way, up 1 over 1 this way. So I have the rough outline of the shape of my absolute value graph, that V shape that we know it should have. Since there's no line or no equals to sign, I know I'm going to have a dashed line. So I'm going to do a dashed line to make the V shape for my absolute value. And then that part is done. So I've plotted my vertex, I graphed my boundary line. I know it's supposed to be dashed because it's not equals to. So then my last step is going to be to shade, and this follows the same rules. If y is by itself, you shade above, or if it's below, or if it's less than, you shade below. But so y is greater than above, y is less than below. But you can also use a test point. So again, for the sake of example, I'm going to use a test point, though I know since it's y is greater than, I'm going to shade above in this section. But for the sake of example, if I chose 0, 0, so if I tested with the point 0, 0, I'd get 0 is greater than absolute value of 0 minus 1 plus 2. 0 is greater than the absolute value of negative 1 plus 2. 0 is greater than 1 plus 2, since the absolute value of negative 1 is 1. So 0 is greater than 3. That is false. Shade away from 0, 0. So in this case, because I plugged in 0, 0 and it didn't work, I know I need to shade away from it. So I'm shading above right there. So that's all we have for today's notes. Make sure you write down any questions, comments, or concerns you have so we can go over them together in class.